So who all has read or started reading chapter 2?
I just received my book today, so.
Okay. And then who is like, oh man, calculus right off the bat? I don't think that we're going to have to do any calculus.
Yeah.
There will be probability because those questions you actually really need to know. Right? This is not an electrical engineering class, right? So I don't expect that, you know, you have to actually know how to do like a Fourier series, which is what that calculus was for. But you do kind of need to understand why it's relevant because it leads to everything else, right? So don't be freaking out about the calculus. You can freak out about the probability because we will have to do that because it actually is an integral part of the class. The rest of it would be just like regular algebra, right? It's simply, you know, the question asks for an answer and you have to figure out, oh, okay, well this is Shannon's equation for noise, right? Signal to noise ratios, and this is why the bandwidth is this, right? So last week we left off on the OSI model and the other layering models. I want to cover those right quick so that we can. Yeah.
Well, this isn't relevant, but I always talk about signal to noise ratio at my work, and I don't understand it.
Well, we're going to understand it today. We are definitely going to understand it.
But they say the higher it is, the better it is.
Huh?
The higher it is, the better it is.
Yes, the higher the better. Yes. Because it's a ratio. You want your noise to be very low and your signal to be very high, right? So let's talk about the OSI model, and then we'll put that into real models, and then we'll have a basis, and it will kind of like lay out, other than the networking security, which messes with the entire model together, because for security you actually need to be able to look through the layers, right? It messes up the entire abstraction model. But for the most of the class, we'll be following that model, and we'll work our way from the physical layer up to the application layer. So in the OSI model, there's 7 layers. Anybody tell me what those are?
Physical,
application,
data.
So here's physical, right?
Yep.
And this is all in your book. Don't need to write it down. Sit with pretty pictures and not Jason's drawings. Or apparently you can go look at the video.
Data link?
So yeah, what's the next layer?
Data link? Data link?
Data link. What's the, well, before we go up there, what's the physical do?
Wire.
Yeah, it is signals across a wire. We're going to cover that today. And Wednesday, right? This is signals. This is the only real layer. Everything else is abstract, right? And then we build everything. And then what's the next one?
Data link.
Data link. What's the data link do?
Managing frames.
Manages frames, right? And the next?
Transport.
Network.
Network. Can't get to transport yet because we need a way to like, where this is a, basically I told you this class is all about packets, right? And we need packets to move from one place to the other and choose which way they're going.
Yep.
Or have something choose for them, right? So that's the network layer, and I just said what it was for, right? What's it for?
Packets.
Packets. And the next?
Transport.
Transport.
Transport. What's transport for?
Segments.
Reliable delivery.
Huh?
Delivery.
End-to-end delivery. So, when we send a message across the network, right, most of the time, when we think of networks, we're sending it from one place to another place. There are networks where we send it to one place to multiple places, we broadcast it. But most of the time we're saying, hey, I want to send you a message, and you want, in a connection oriented, you want to receive a message back like, hey, I got your message, right? And a connectionless, so you just rely on the network to deliver it, right? But this is end to end, right? We want an abstract, this is what this is the layer computers talk to computers, right? Everything else down here, you're really talking to routers, talking to switches, or you're talking to a wire, right? This is computers talking to computers. What's next?
Session.
Session. Does anybody know what the session does?
Catches.
Well, for like for TCP connection, for instance, just creates the session. Creates like a pipeline. Does that make sense?
So the session and the next layer, which is the presentation, are really usually tied in real life into the application layer. Right? The session layer was, I guess in the book it says, manages task dialogues. Right? So your task is you're going to bring up a web page. Right? That web page might consist of HTML, right? Might consist of, almost probably consists of some kind of streaming ad service, right? It's a session, right? There are multiple things going on, and that was the idea. Remember, the OSI model was developed after the internet was already up and running, right? So this is after the fact. But it wasn't designed on top of the internet. It was like, hey, if we were going to design a perfect network, this is kind of what it would look like, right? So it's not unimportant because we still model things to it, right? But these are the things that we know that we have to segment out. So the session manages task dialogues, and then presentation converts presentations, right? But all this stuff is almost always handled in applications, in the application layer. Right? When you do HTTP, right, it tells your browser to do things, and it doesn't. So, this is the applications make it worthwhile. Everything else is computer to computer. This is node to node. And then as we start exploring physical, we'll see why data link and physical get connected together. And we deal with that. So what's the real internet look like?
As opposed to the fake one.
Just mess.
So this is theoretical, right? What's the model look like for the internet?
TCP model, IP model.
Well, certainly IP, right? So we have what at the bottom?
Physical layer. It's a 5 layers. So
And we just usually call this physical. And that actually contains both the data link and the physical model. What's the next one? Network. And in the internet, that is what? The internet, network, or IP layer. The internet is IP, right? There's no other networking protocol that runs on the internet. Otherwise, it would be the internet.
BGP, ISIS, EIRGP.
So yes, right, but those are different network layer and physical devices. If it doesn't use IP,
Those all go up to network, all layer 3 of the OSI model. All those I just quoted go layer 3 of the OSI model.
okay,
And even some of them.
So I-
Go to the transport network, so.
Yeah.
Depending upon-
But if I go and I buy a core switch from Cisco,
Sure.
right? And I'm gonna put this in some kind of trunk system to actually manage internet data. What does that run on?
The iOS?
No, no.
You mean, so what is it?
What layer?
So what is the router doing?
Yeah.
It is routing or directing IP.
Mhm.
However, though, there's management protocols that they use, that are used on the internet just as much as IP is, if not more.
Yeah. Yeah. I can see the point. But the internet that we think of today, when we talk about internet and moving data from place to place, is all IP.
I don't like using, personally, I don't mean to belabor the point, don't like using the term internet, because it's like saying my modem, my cable modem.
Correct.
Well, it doesn't modulate and demodulate. It's that cable device is a device, it's not a modem, but we call it a cable modem.
Uh-huh.
So when you say the internet, I mean, that's a very large nomenclature, large description. So when you say this, at this layer here, in the TCP, I mean, PPOP, it's a protocol that's most used on the internet. I know, right? Arguing semantics.
Okay. We'll leave it at that then. What's next?
Transport.
Transport. And
Application.
application. And I showed this on the model last week. Right, all of these actually map out to this, right? Where IP is,
five.
huh?
You're not sales off 4.
It's just 4. Right, and this is the same diagram as that, right? Where you squeeze IP in the middle. All right. Now, let's start talking here. So we're gonna start going our way up this direction, then we'll talk about other things that. So just talking about the physical network. We're going to send a message from one node to the next. What are ways that we can do that?
Wires
Let's
to
just
one.
assume there's a wire for right now.
Is it just a copper wire, or could it be a fiber?
Gold.
It
It could be wireless.
it could be, well, let's not do wireless yet because then we introduce other problems. But
Light.
huh? We could do light, right? So, and then it would have to obviously be fiber, or we could do voltage or something across a copper wire, right? We can modulate amplitude and frequency, right? And send a message across a wire, right? Now, our message, because we're dealing with computers, let's say we want to send 011000010, whatever that is. Right, and we want to send that across the wire. Right, the problem is this wire is not digital. Right, this is an analog, this is physics, right, and physics is analog. So how do we send this thing across the wire? If we're doing it really slow, right, let's take the light method. I think that's actually a great method, right? We can do old-fashioned, right, Morse code, right? Turn the light on, turn it off, turn the light on, turn it off, right? That works really well for slow messages, right? It's not going to transfer, you know, it's not going to deliver your MP3 file very fast to your computer, right? So then we just speed it up, right? The problem is to our human eyes, turning the light on and turning it off looks like this. But when we turn the light on and turn it off, does it instantly come on and instantly go off? No, right? So there's little round edges. On top of that, right, what if we want to And if we speed it up, right, then the round edges become bigger because the light is off more of the time. And on top of that, there's attenuation, which means the light gets dimmer as we go down. Now, light is a great example to start with because it takes a really long ways for it to get dim. And when it arrives there, most of the spectrum of the light is the same amount of dim. Now, let's do it with, how would we do it across a wire?
Converting it from analog to digital, digital to analog.
But that's what we're doing.
Okay.
So how do we send the signal across the wire?
Voltage.
Let's do voltage, right? Like no volts and maybe 5 volts. Right? And we do the same thing. The problem now is it is less fast than light, right? It ramps up. And the voltage isn't quite exact. Right? Because there's noise and stuff in here. So we start making our picture worse. What else could we do?
You use different frequencies.
We could do different frequencies. That's kind of the same line of voltage. We can also, for the electrical example, we could change the amperage, right? So same amount of voltage, but then so the volts now go, or the volts, let's say, are 5 volts, and it goes from 0 amps to like 1 amp, right? And we kind of do the same thing. Now, let's say that we want to use frequency, right, to stick this in this wire. Then how do we make something, the frequency is a wave, right? How do we make this wave look like that?
Doesn't have anything to do with the SNRs.
We're gonna get to signal to noise ratio.
Turn it on for a while, turn it off.
No, right? That's something different.
Phase.
Do like Fourier stuff and just add a bunch of them together.
Yeah, we start adding waves together, right? So if we take a wave, it looks like this, right? And it's definitely not going to end up looking like that. But let's say then we do another wave that looks like as bad as that is. When these waves are combined, what do they start to look like? Right? It's a sum, right? So this wave starts to look like this. It's really, actually, it's higher here, right? And then it kind of goes to nothing there, right? And then it gets a little bit here, then a little bit there, a little bit there, and then goes really high again there, right? And so we can start combining waves together. And as we put those waves in there, we start doing all the harmonics from adding all the waves together, we can start approaching something that looks like this. And the nice thing is that this is a Fourier transform, and it was figured out, obviously by a guy named Fourier, and it uses calculus, which we do not have to use. Right, but we need to understand that we can add waves together so that we can create a wave that looks like that. And so now we can use frequency modulation and adding these waves together to put into this pipe our digital information. Now the question is, out of is how many transformers you need to use in the series to get your optimal data. So if we have a wave, I'm going to use the example so it looks somewhat right. That really represents our data, right? Because if we put our easily represents our data, right? And then we put a dividing line here to where anything below the line is 0, anything above the line is 1, right? And then we use timing to take when we're going to take that measurement, right? So timing's here, 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 here. So, but if we use less bandwidth, right? Every time we add a new wave, we're consuming bandwidth.
I'm sorry, so the device spits out multiple waves simultaneously? Or is it, I guess I'm confused as to when all that happens. Does it come out like, oh, here's the first one, here's the second one, here's the third one?
No, it all happens at the same time.
Okay.
So, like, if you shoot light across light or whatever signal, right? Everything travels in a wave. You shoot it out at the different wavelengths at different times. They combine together, right? So, did anybody remember like the high school physics experiment where you move a mirror in a laser beam and it actually cancels itself out? The laser beam disappears, right? So, you have a wave, right? It's a laser, so the wavelengths are exactly the same and coherent, right? If you set a mirror at the right exact spot, right, then the wave combines like this, and the net result is nothing. But if you shine a different color light, right, then the waves combine and you start getting wild things that look like that we can actually use in digital communication. But there's a limit, right? So the limit is, hey, this is a great one, but every time you add a new frequency, you're consuming bandwidth, right? And you would like to use that extra bandwidth to send other signals down there so that you can fill up more data, right? So if we had a signal that in the example, by the way, in the book, this is 8. This is 8 frequencies to create this one. If we have that and make it look with 4 frequencies, it's not nearly as nice, right? But if you look at our model where we just say 0 and 1, right? It still works, right? Even if in this model, right, we have a really high 1, we have a really high value of 1, and in this model, our value of 1 is lower.
Sorry, are we quantizing in the frequency domain? Is that what you're
Yes,
saying?
in the frequency domain. This is frequency modulation.
Right, but we're trying to quantize it.
Yeah, we quantize it in a simple binary manner, right? Is this a 1 or is this a 0? And then if we have that again, I think it looks like that, where a line is like here is not nearly as good, right? So in the ideal world, right, this is what we want. We can make a better representation of our binary signal, but we want the absolute minimum best or acceptable method, right? Because if this takes 8 different frequencies to create, this one takes 4 and this one takes 2, this one's out because it doesn't work, right? This one is acceptable, but it takes double the amount of bandwidth as this one. So we would rather use this one. Accepting the fact that when we do things like this, sometimes we will get errors. And then we put error correction on top of that, or error detection at least, and then just retransmit, right? And the reason we do this is that we have this broad range of spectrum that we're sticking in this wire. And if we want to maximize the use of the network, then we want this to be the smallest acceptable number of frequencies, because that frequencies add up and take up the spectrum of the pipe that you're shooting it through. And then if we have stuff left over, then we can send more signals, right? And keep and fill more data in there. Right now we're sending one datagram, but we can send two, right? So, the problem is with less with fiber, more with wire, is what happens over long distances of wire.
Get lost.
It attenuates. What's attenuation mean?
Get lost.
Right? The signal is weaker at one end than it was when it started. This would not be a problem if like let's say in this example up here, right, the signal was only weaker. Right? If this is the exact same signal with a different amplitude, right? The signal is simply weaker. So attenuation wouldn't be nearly as big of a problem, right? We simply have to measure this more accurately. The problem is that this is not what happens. What happens is some frequencies attenuate more than other frequencies. So, in our example that we had up here on the board before, right, where we're combining waves, right? Let's say that the higher frequencies attenuate more than the lower frequencies. So that means that our transform that's ending up at the end is now different when it arrives. Like the shape is no longer the same because some wavelengths attenuate more than others. Right? So that's one of the things that happens. What else happens?
So you saying the higher frequency attenuate more?
No, I think it's actually opposite, but it doesn't matter. What it really matters is that that they don't attenuate the same. Right? If they don't attenuate the same, then our frequency modulation gets jacked. Or what waves look like when they come out at the end is different than when we left. They're not just simply smaller; they're different. What else happens over long distance over wire? Noise. What's noise? The cosmos talking, right? It literally actually can be that, right? It's the cosmos talking. You generate thermal noise when you're pushing electrons through a copper wire, right? You have outside interference that's happening, and we'll talk later on how you compensate for that. So you have outside interference, right? You have is noise. So our wave, even though we put it into the pipe, doesn't actually look like that. Let's choose this one now. It looks like this. Right, and it's not that big a deal if it's a little bit of noise. Right? But the noise at the end of a long pipe, remember, is the same as the noise at the end of a short pipe. Right? So in this one, even if we had this perfect wave, which doesn't exist, you know, the same squigglies start to make really giant differences. What else happens? How fast does it propagate from one end to the other?
Speed of light times some, whatever your.
Some fraction.
And yeah.
Yeah. It's definitely not a whole number or bigger, unless it's one. But right, it propagates. There's a propagation time. Right? Huh?
Depending upon the media.
Depending upon the media. Ironically, wireless is almost the speed of light. Very, very close to the speed of light. Right? Wired is, anybody want to take a guess what about it? It was generally considered a good number.
80 to 90.
0.83.
Yeah, it's generally considered 2/3. Most of the time that doesn't matter because when we talk about bandwidth and or when we talk about latency, the speed of light's pretty fast, right? So ironically, it's not fast enough. It would be we run into barriers all the time with the speed of light, right? We consider it, fast, but in computers are fast enough now, networks are fast enough, that speed lag is actually an issue. Right, so 2/3, what else?
Isn't there like mechanical limitations? You wanna talk about that? There are mechanical limitations, in other words, how fast you can produce a signal.
Sure. Yeah. So that's a little out of order, but yes, there are mechanical limitations on how fast you can produce a signal. The greatest example of that is with fiber. When we go into fiber, fiber has such an incredible amount of bandwidth, right? And it's simply a mechanical limitation of being able to stuff light into this thing fast enough.
Affect
Huh?
quality? Does it affect the quality when it gets interrupted like that?
So that's pretty much, I think this is a pretty good example or representation of like the physical limitations of sending information over a wire. Generally, when measuring hey, I got this copper wire, what is the bandwidth of my copper wire from a physical property perspective? What's the bandwidth of it? Right? The bandwidth is, hey, I can really stick a lot of information in a copper wire, right? The problem is as I get further down the bandwidth spectrum, right, some of that stuff becomes highly attenuated very, very quickly. And if it becomes highly attenuated very, very quickly, then it's not much of a use to me, right? Unless it's some short span, right? So if you look at like the bandwidth of a processor to memory, right? The attenuation on that's really, really high, but if you only have to go 10 microns, then you can stuff a lot of information in that, even if it's highly attenuated, right? Compare that to Ethernet, where you need to go 300 feet, right? 300 feet is the attenuation. Actually, though the same copper wire or the same copper material that you put in this etching, you're using in this wire, right? The problem is the distance, right? So it doesn't really have the same bandwidth from a practical perspective. We have to cut some of it off because the attenuation is too high at certain frequencies, right? Oh, and of note, what are we going to define bandwidth as? So bandwidth in electrical engineering is actually measured in hertz, right? It is a frequency, just like we were talking about. Bandwidth in computer science, which is really what we're concerned about, is measured in bits per second. It's a capacity of data going across, right? So, and they're related, but they're not exactly the same. So they're proportional to each other, but because the electrical engineering guys can't overcome physics, right? So bandwidth is a hard number. We can be clever at computer science and make bandwidth out of something, but it's still proportional, right? There's upper limits to what we can do.
What was it measured then again?
Huh?
What was it measured in again?
Hertz.
Hertz per second? Or
It's per
No,
second.
hertz is a frequency measurement anyway.
between computers?
Yeah, hertz is a cycles per second, so
Mhm.
it's already per second. All right. So now let's talk. We talked about being able to manipulate whatever frequency we want, right? Because it's a wire, so we can put whatever we want on that thing, right? Not so the same with what? Name some things that we can't go willy-nilly with the frequency. Wi-Fi. Why can't we go willy-nilly with Wi-Fi?
We've been
regulation.
Yeah, because the government comes after you, right? So you can't go willy-nilly with Wi-Fi. What else? This is not nearly as intuitive, right? We can't go willy-nilly with fiber either, right? So fiber is actually opaque to certain frequencies. It doesn't shine through, right? So what the frequencies that do shine through turn out to be really, really high frequencies in the grand scheme of things. And like visible light is of a high frequency. Microwave that Wi-Fi uses is a high frequency. And so this adds different problems, right? So the problem is if you have a super high frequency wave, then how do you encode information in that?
Disperse it?
But if you got you can have in your bandwidth, let's use Wi-Fi because that's government regulation, right? It's very narrow, right? So you can have waves that look like this to waves that look like this. So it's very narrow. So doing a whole lot of adding more waves to it to do transforms and stuff become also difficult, right? So how else can you do it? Amplitude, right? So let's make this down into it, right? And then we change the amplitude. And we can do other things too. But so this looks very much like a binary communication, right? So we're changing the amplitude of the wave, and this wave that we're sending the changing the amplitude to is your carrier signal, right? And you can also embed other things inside your carrier signal, like timing, right? If you're broadcasting at a fixed frequency, unless you're on a spaceship going really, really fast, right? Then the frequency is very, very close to what it was when it left. So, you know, the red light, blue light shift is not very big for this, right? So you can use it for timing. There's other things that you can use for it. So this is a carrier signal. But doing this with wireless gives us some other problems. So remember last week I drew, like we have this mesh of networks, this wire, and then we think of like, if we're talking to an access point, in wireless we think of it looks like this. But it doesn't, because wireless is a broadcast medium, right? It actually propagates out a signal that encompasses the access point, but it also encompasses this other computer. So it's not really like that. So when we talk about that from a physical perspective, what's the problem? Other than stepping on somebody.
Will it slow everyone down?
Well, it does slow everybody down, but the question is why?
The amount of noise you're introducing creates a lot of errors.
Yeah.
Cancellation.
So you don't have walls between the computer to block signals, right? All the other signals are propagating to everywhere else. It turns out that in the microwave band, things attenuate pretty quickly. Literally, this is a logarithmic scale. It can be 1,000,000 times difference from here to here. So we're in the wireless band, we're transmitting like this, right? That means that if we're sending this signal, right, it starts out looking like that, right? It gets smaller and smaller and smaller and smaller as it gets down, right? And this one does the same. So the thing becomes is how do if this computer can interfere with this computer and this computer can also interfere with this computer, how do we actually manage that? Well, one thing that we can do is since it attenuates very rapidly, at a certain point, it is no longer any better than the noise. It's so attenuated that it's no better than noise, right? And let's just call that like here and here and here and here, right? Below this line right here it's no better than noise. By the way, why is broadband or Wi-Fi in 5 gigahertz, 2 gigahertz, 2.4 and 900?
Free?
Huh?
Government regulation?
It was government regulation. It was government regulation. Government said in, I believe in the 80s, hey, this stuff is so bad, nobody wants it. There's so much interference in these bands, nobody wants it. So we are going to open it up to hobbyists and companies to do whatever they want with it. And that's what happened. And the first thing that took advantage of it was phones, right? So you got wireless phones.
Yeah, wireless phones, I'm sorry, yes.
Yeah, wireless phones, right? Like the old AT&T brick-looking phones, right? Not cell phones, like the
We're talking
ones,
home.
phones, like the extendable antenna that always broke off, right? So, but it was so noisy that nobody wanted to lay claim to it, so the government opened it up, right? And this is what we run our computers on. But because of it was so noisy, right? Ways to deal with that noise were the innovation in that particular space was very rapid, right? And now we have a large body of knowledge in computer science and electrical engineering that's centered around how to deal with noise and how to deal with interference, even if it's from yourself.
So how about if we have multiple channels? Like
So, multiple channels, that's where we're going. So if you're running 2.4 gigahertz, right, and you ever decide you want to go mess with your router directly, right, you can pick different channels to put that on. So most of the time that's auto-negotiated. They listen and say, hey, this is not very noisy here, so I'm just going to pick that, and then your other router says, hey, it's not very noisy here, so I'm going to pick that, and so on and so forth. Go ahead.
All routers automatically choose 1, 6, and 11.
Huh?
They all choose 1, 6, and 11.
You would hope.
You would
they
hope.
all Pick
You
1,
would
6,
hope.
or 11.
The problem is,
This
like,
is
what
not-
happens if you're, you have a close neighbor, you're in an apartment complex, there's all sorts of things that interfere with this, right? So, but there are channels, right? Because we do have, it's not that we don't have any frequency to mess around with, we just have a little of it. So we have to deal with it in different ways, right? So this one, we'll do 1, 6, and 11, right? One thing we could do is we could do 1, 6, and 11. Right, which is just different, it's a different frequency. It's really close to the same frequency, but it's different, and it's different enough that it's easily picked out of your microwave that's leaking.
There are channels within the band.
Correct. So, but we don't have to do 1, 6, and 11, right? Because this one attenuates right here and disappears, and it's no longer out of the noise. And this one attenuates here and disappears, so it's no longer out of the noise. So technically, we can just do 1, 6, and 1, which is much more convenient. And so then what we can do is, if we have more than 2 choices or 3 choices or 4 choices, we can start building grids. And you can build actually quite a number of extensive grids on just a few number of channels inside of that band.
A lot of people, sometimes I've seen it happen many times, they actually are better if they're not on 1, 6, and 11 because all the neighbors are. So if they get off 1, 6, and 11, it helps them a lot, some
Mhm.
people. I've seen that happen like 100 times at least. So.
The other problem with wireless.
Sunspot activity. Sunspot activity.
Oh no, this is more insidious than this. Let's just call this the phone, and this is the access point. Right, your phone is going to connect with the access point. And this down here is just environment. But the problem is that it's a reflective environment. Okay? So what are the paths to the access point?
Straight across and then down top of circles.
Right here, right? And then right there. Now, maybe it interferes.
Sometimes it's additive.
Sometimes it actually adds. It makes your signal better. Why?
Because if they're in phase, when you get.
If they're in phase, right? Remember I just showed you the thing of the laser, right? So if you have a wave like this, and you have the exact same wave because you broadcast it yourself, right? And it looks like this, because it's in phase, what's the result? You double your amplitude, ish.
When your timing be out?
A little bit, a little bit. What's the length on wireless?
Over 2.4.
Huh? No. Like, how far can you be away from an access point before the wireless no longer works?
It depends
100 meters.
It depends on what it depends what bandwidth and what standard, right? There's a timing in the standard that says, hey, you can't go beyond this.
I was able to 2.11n.
Yeah. But relatively, the point is that it's relatively small, right? You're not broadcasting wireless from here to New York City, right? And you're reflecting off Pikes Peak, right? It's relatively short, right? So remember, this is what it looks like. So yes, it is slightly out of phase, but the speed light still in this particular is pretty fast, right? So it doesn't look quite like that, right? It's shifted just a tiny bit that way, or in our reflection case, it's shifted a tiny bit backwards. It doesn't matter for the signal, right? So if you look at like this, your signal, right, is shifted a little bit backwards, so it's really big, and then it kind of gets a tiny bit smaller, and then goes to flat again with noise, right? So it can make it better. Now I move my. What's the width? Anybody know offhand what the width of microwave actually is? It's very small. So I move my access point 2 centimeters or something, right? Something incredibly small, right? Because the width of the wave is very small, and now, so the speed of light is very fast. So moving it 2 different distances doesn't pull it out of phase a lot, right? But physically moving it, right? You're moving it in the width of your wave right here, which is a microwave, which is above visible light. So it can now do the exact opposite of what we wanted. We get something like this, and you get no signal, right? Or very little signal, right? And literally, like when you're doing these kind of experiments, there's like 1 million times difference for moving these tiny little places. So then you have to deal with that, and that's called wireless multipath. All right. Now, let's go back to we talked about some of the problems with signaling, or other problems. It's not just trying to get a strong signal from one side to the other, or an analog signal to look like a digital signal, right? Or even just dealing with interference, right? There's other problems with sending stuff over the wire. So, we're gonna send it from client to client again, right? This is our wire, and we want to send something like it was before. Right, we want to send that over the wire. But this is really a sequence of bits. So how, this is kind of inefficient. How could we do this better? Like, let's say we've worked on all of the modulation, whatever, or the physical problems. How can we cram more information in this?
Multiplex,
We can multiplex, which is
more than one signal.
more than one signal, right? What else? What if we have more than just ones and zeros, right? So if we can represent this as 0 and 1, right? There should be a system that we could represent as 0, 1, 2, and 3, right? And we can cram more information in there. So long as we can pick it out at the end. There's attenuation problems again, right? With our voltage, now we have real big attenuation problems, right? Because as the signal gets smaller at the end, picking out what is 0, 1, 2, and 3 becomes even harder. Right? But we could cram more stuff in there. What other problems do we have?
Timing.
Think about, timing. Did you read the book?
Smart, I guess.
The problem is timing, right? Making very, very accurate clocks is super expensive, right? So there becomes a point where the clocks aren't exactly in sync. So we have a timing problem, right? And one of the things that is crazy is that computers have some of the same problems like a human has. Quickly, how many zeros are in there?
Oh,
14.
Whatever, I don't. Right, the problem is that long sequences of a 1 or 0 become difficult for a computer to distinguish. How do we fix that?
Break them up.
We could break them up, but remember, we can only send 1s and 0s across it. So one of the things that we could do is like our 0, 1, 2, and 3. Like every time we send a 3, that's like a break, right? And so we resynchronize. So we can put data into the network to synchronize it, right? The other way that we could do it is that we could eliminate large sequences of zeros. How do we do that?
Encoding.
Huh?
Encoding.
Some kind of encoding scheme, right? So we could create a table that says that consumes 5 bits, but it only has 4 bits of input. Right? And then we have this table that always maps things to something that doesn't have a lot of zeros. So let's say that we do that, and we come up with a table that we put 4 bits in, right, and 5 bits pop out, and that way there's never more than 3 zeros. Right? Everybody can conceive of that, right? That would be perfectly possible to take 4 zeros and stick them in, and then you'll never have, actually I think you can do it with only 2 zeros. Right? You can construct a table that has that. And then we just reference that table and we say this is a standard. Right now, we put this stuff in and it looks like, so this 4 bits goes in, right? 5 bits comes out and it looks like, right? This 4 bits goes in, 5 bits comes out and it looks like and I'm just making this up, right? I don't really care about the table, right? I'm not gonna make you do that even in your homework. But there is a table that's called this, and it's called an NRZ table. It's a non-return to zero table. And it actually does this transform. Now what's the problem? Now we have a long sequences of ones, right? You can see that this table is going to spit out more ones than zeros. Now you could have long sequence of ones, which is the exact same problem. Exact same problem. How do we get rid of that problem? You could say, oh, I construct a 6-bit table, right? But now you're starting to consume a lot of information, you know. So what else do you do?
Do like a Manchester encoding where every time the bit flips, it represents a
Correct.
piece of data.
You start inverting, right? Every time that you hit a 1, you invert the signal. Zeros become ones become zeros, cats and dogs together, right? So now what this signal was something like this, right? It's gonna be hard to tell because I drew it really small, but. And then our next frame looks like this. So now we have long sequences of ones that we need to get rid of. So every time we encounter one, we invert. Right? So now you get, so 1, it comes up, it's like, oh, it's a 1, goes down. Another 1 inverts, right? 0, oops, inverts 1 down, and so on and so forth. Right now, we are no longer we have not a pseudo-random, but it's very widely dispersed, right? And we have very little things that come in a row. And one of them is Manchester encoding, one of them is NRZI, one of them is scrambling. There's a number of ways that you could do that. But the idea is inverting the signal. And this particular one is called 4B, 5B, inverted 4B, 5B. So 4 bits in, 5 bits out, and you invert, or in RZI. So, all of this that we've been talking about so far with encoding, this all works all well and good on baseband. Stuff that you can modulate the frequency at will, right? But in fiber and wireless, which is passband, it doesn't work so well. So the ways to do modulation in passband let's just go ahead. Right, we want to send this across the signal in some bandwidth which is fixed. Right, we have some bandwidth ways that are fixed, right? We can do amplitude keying, right? Which is where you change the amplitude. So if you have a wave like this is our carrier signal, right? And you want to change the amplitude, right? You simply add to the wave. I should have drew this bigger, but yeah, this is not very good. But you get the idea, right? You add to the wave, blah, right? You make it bigger, add more power. What other things can we do? We do have some bandwidth, so we can change the frequency. right? We change the frequency, and then it becomes representative of what we want to do. And what's the other one, which is not nearly as intuitive?
Phase.
Huh?
CDMA, timing?
Phase.
Coding.
Well,
BPSK, QPSK, and all
yes,
phase.
yeah, you do key shifting, right? So we have a wave. This is harder to draw. It's the worst. And this probably doesn't look exactly what it's like. Right, you flip the wave upside down. So now you have a single signal, you simply move it back a half wavelength, right? It is now upside down, right? And then you move it forward a half wavelength, and it's now right side up. Move it back halfway, so on and so forth, right? And so what it looks like is this, right? Where you're getting mirror images.
So I have a question. If we combine the baseband signal with the passband signal, they can interfere each other since they have different frequencies.
Correct. So that actually happens. It happens. So the question was, can you combine a baseband signal with a passband signal, and they don't interfere with it? Sure. Most of us in this room probably use that. You want an example? Cable. Cable modems deliver TV to your house, right? And they do that in fixed increments of about six megahertz, and they deliver a signal to your house, right? And then they decided, hey, I would really like to sell internet because this cable thing is super regulated and I cannot make as much money as I want. So I'm going to sell internet. So the question is, how do you do that? You had a cable and you delivered that. And so you have a fixed spectrum. You have you have your bandwidth, your spectrum down here that's going across that, right? And then you have some of this stuff is for management, whatever. And then you have like TV. Remember last week I said TV. It's the same in cable as it is. No, we're talking early cable, so analog cable, right? So they've since made it digital. Why? Because they can stuff more things in there, right? But you know, TV is very big, right? It was big in cable also because analog cable came to your house, and unless you were dealing with some of the stuff that outside the regular TV, right? It just hooked to your TV, and your TV interpreted the signal just like it came out of the air, right? And these were all in 6 megahertz chunks, right, for all the channels. But you have all this stuff over here, right, that nobody used, and so then they started using that. They had to do some modifications to their network, right, because the early cable networks were one way. And so they would amplify and use one-way amplifiers to get the data all the way out to your house over the cable, right? But now internet's not one way, right? You obviously need to be able. And so what do you think was the first solution for that?
Synchronous signal?
Oh, no, that was the second solution. The first solution.
Was it filter?
Huh? That's ADSL, put the filter on there, but you're also getting there. So is anybody heard of like satellite internet?
Yeah.
Right?
Yeah.
Everybody's heard of that, right?
Yep.
How do you transmit upstream to satellite internet?
So
Huh?
You have an LND that sends out this signal.
Yeah, no, yes. For small scale, we're gonna have satellite communications at our house. How did that first happen?
Oh, they send it back through telco.
They sent it back to the telco.
Yeah.
They sent it back to the telco, right? So when you sent something upstream, it went through your phone lines, and when you got stuff downstream, it came over cable. And the reason is because all the amplifiers that were in cable were one way. They were meant to shoot stuff one way, right? And so then the second solution was to make two-way amplifiers and do it asynchronous. And it's still that way, right? Where you use some bandwidth down here, right, for upstream, and then this bandwidth up, it doesn't really matter where the bandwidth is, but right, your bigger bandwidth, right, and then you also don't need the same amplifiers, right, because they're in a way different spectrum, and so they don't interfere with each other, right? So this is how cable modems work, right? They're not modems, right? They're devices that at first allowed streaming stuff to come down to your computer. Now they allow it to go both ways, and they are a shared resource. Why? We talked about this last week. Huh?
It's an aggregate.
It's an aggregate, right? It's really one wire that goes out to, and you have splinter wires that go off to your house. You probably have splinter wires in your house, right? You have some that go to your TV, right? Some that went to a TV that doesn't exist anymore, right? And one that goes to your modem, right? Which goes out wirelessly or wired to the rest of your house. So your modems, cable modems actually also a switch, right? It handles networking inside your house. So, and then cable modems have this one coax wire that goes out to the neighborhood. And what they did is the early cable networks had all these fiber trunks, and they put these fiber trunks out in neighborhoods, and then they ran a cladded wire out to around the neighborhood, and then they just splintered off this wire. Well, the easiest solution was like, hey, this is already in place. Let's do the asynchronous thing. The next one is let's change the amplifiers, and then the next one is like, let's start running more cables to people's house. Because we already have this giant fiber trunk that's sitting in this neighborhood that we built when the neighborhood was put up or afterwards, right? This thing basically has not infinite bandwidth, but it's really big, right? It has lots of capacity. So then they started, instead of having this wire that looked like you know, like really old Ethernet, right? That went off like this, right? They started running wires directly to this. And you start getting these bigger and bigger and bigger. But there's still, it's not every house, right? It's there, but it's not as many houses as it used to be on one wire. So let's talk about limits. There are physical limits for how much stuff you can put in a network, right? Because you can't overcome physics. Intel tries all the time. They're only mildly successful. So, if you have a network or have a signal, and why this not quite even, let's say we have a constant frequency signal. How many samples can we stick in there? Not data, samples.
2 times.
2 times. Why 2? Yeah, Nyquist, right? We can send 2 times the samples. Samples don't necessarily translate to data because we've talked about already is like, oh, we can send 0, 1, 2, and 3 in there, right? In a noiseless system, a system that had no noise, which doesn't exist, what's the bandwidth of this type of signal? In a noiseless system, a system that has 0 noise, right? We can get 2 times the samples, right? So, but the question is like, is two times the sample rate, right? Because you can put 2 times in there. But how big, if you have a noiseless system, how big can your sample be? It can be arbitrarily as big as you want, right? If you add enough power to it, right? There's no noise. The bandwidth of the noiseless system is infinite because your sample can be any size you want. The problem is that we don't live in that world, right? So then we need something that deals with noise. So, the easiest way to visualize noise is, let's have our 0, 1, 2, 3 system right here. Right, and we have some amount of noise that sits in here. Right, it can be anywhere. It doesn't have to be this place in the graph, right? It can be anywhere. And unfortunately, it can vary in size. Right, but we do have some nominal measurement of noise. So we can predict what the noise is on this medium and in this environment. Right, so if the size of this is the same width of this, how much stuff can we put in this pipe?
Half your capacity.
About half your capacity. Why?
What the noise level can take up. Well, remember the noise number, you've only indicated one possible amount, but it could be, that could be affecting all of your different.
Yeah. So, but let's say that this is a nominal measurement, right? A measurement that we've taken this medium and in our expected environment, we measure the noise on it, and this is about what it is, right? Over some period of time, right? We can measure that, right? And then, and this goes back to what your question was earlier, is what is your signal to noise ratio, right? And your signal to noise ratio is called your Shannon or your Shannon capacity. And it can vary widely. So it's normally used in a logarithmic scale. So your Shannon capacity, or the amount of stuff that you can theoretically put in a pipe. Not physically, this is your theoretic, like, or not really, this is your theoretical limit. You can never get past this. This is, you built the perfect network, is reaching your capacity. And that is your bandwidth, and we'll do log 2 because we're measuring things in bits, times 1 plus your signal to noise ratio. Over, obviously, time. So this means that if your signal to noise ratio is better or worse, you get more bandwidth. Bigger. Right? What you want is you want very large amount of bandwidth and then some nominal measure of noise that can exist anywhere in this bandwidth, right? But you want the noise to be small. I mean, it's very intuitive, right? But that is intuitive. This is absolute, right? This is as good as you can get it. Now, signal to noise ratios are almost always measured in decibels because decibels are conveniently a logarithmic scale. So a signal to noise ratio of 1,000,000 to 1. Is how many decimals? It's log 10, not log 2. You just count the number of zeros.
6.
No, well, count the number of zeros and add
60 decimals.
truncated or append to 0. It's 60 decimals.
Oh.
So when you hear about
I know see them above 46.
huh?
I think 46 is the highest I've ever seen.
A signal to noise ratio?
Yes.
No, like you could transmit data through that table, and I guarantee that the signal to noise ratio is worse than that.
I mean, that's the very highest. That's the very best I've ever seen. At
No,
the
a fiber
most.
would be. I don't know what fiber is, but it's almost at 0.
Talking wireless.
Oh, okay, wireless.
I'm talking going to a cable modem when you look at the GUI.
I think he's just not putting the negative in front of it.
All right. So we have gotten through most of the physical, which allows us to use Wednesday to work through problems that might resemble something in your homework, so that we can put like real data, like we can actually through real numbers. I would like for us to try to keep on that pace, so that the homework isn't overwhelming, particularly those that have spent, took your math in your undergrad that happened to be like 20 years ago. And so that we can build a case for success, at least in the tests and in the homework. So I will use next week, so long as we don't get behind, I will keep that format as much as possible. Any time left in the week for this particular layer, we'll just go through problems.
When are you expecting the first homework to be posted? And
I will put the first homework, it's already done. I'll put the first homework right after we have the class, so that everybody is paying attention to the problems that we're doing in class and not saying, oh, that was not relative to the homework, right?
And how long will we have to work on it? When's it due, basically?
At least a week. Sometimes it might be more than a week,
Cool.
but you'll always get 7 days.
So I have a question.
Uh-huh.
Other than just changing the channels to not 1, 6, and 11 usually because it's only crowded on them, and changing to 5 gigahertz, is there any other idea you have to help people have Wi-Fi interferences or not?
Less devices, the better. We talked about this last week.
Like if they have 50 neighbors, is there anything we can do to help?
Put a Faraday cage around your house?
Yeah, put a Faraday cage. Aluminum oxide paint.
Get to know your neighbor, go over to their house and secretly destroy their router.
Yeah.
Seriously,
your neighbors until they turn off their router.
5 gigahertz solves lots of problems.
But
As
some
long as
people
your
have
problems aren't range.
non-5 gigahertz devices.
Well, that sucks.
So there's something we can do on?
No, I mean, bandwidth is a finite one.
What's that?
Yeah.
Yeah.
It's something different.
Oh.
What's supposed to do?
Same concepts. Same concepts.
What's the last time? That's I'm gonna ask.
Yeah.
Yeah.
Which one we should go for, you know?
This. And the concepts.